computer waiting for people to pop on. He just said that it'll take a little bit of time to get them up there, but they should be up tonight.
Okay.
What are you talking about? The rest of the videos for chapter 11?
Yeah.
They're up.
Yeah.
The rest of them are up now, and the first one for chapter 12 is up, and more of those will post tonight as well.
Nice.
So the quiz is everything that's on those videos is in the quiz.
Everything that's in the quiz is on those videos.
Yeah. That's nice.
Or the quizzes are called reading quizzes for a reason too, right? So the chapters themselves, like you should read those. Don't just watch the video and let that be your only source of truth, okay?
Yeah, but the thing is, my book hasn't come in yet, and that's anxiety.
So Candace, the other thing is I've posted the first 4 full PowerPoints for chapters 11 through 14. So you can look at just the PowerPoints themselves, and that's sort of like an outlined version of the chapters.
Okay.
It's not everything, but it's a really good starting place, right? And I would highly suggest printing out those PowerPoints and sort of taking notes on them as you watch the videos. That's a really efficient way to make sense of the material, at least in my opinion.
That's how I do it.
Yeah, I'm just getting anxious because I see that reading quiz is doing like 3 days. It's like, okay, PowerPoints, print out.
So our schedule says that we're supposed to be talking about chapter 11 stuff tonight. If I look through chapter 11, there are a few things that I see that students normally struggle with. Chapter 11 is actually more or less a lot of review from Chemistry 121. So the shapes of molecules are things that you have already learned someplace before if you've had a prereq for this class. Polarity of molecules is something that you will have learned before if you've had a prereq for this class. But I don't expect that everybody is like fresh as a daisy with those things, because there's some of the harder topics from Chemistry 121. So the things that I think are going to be important for us to do a little practice with from chapter 11, and I'm sharing my screen.
Lefty, huh?
What's that? Yeah, I'm a lefty. Sorry about that. Legit, I one time had a student in my course evaluations say that I should learn to write right-handed so I didn't cover up the material. Yeah, that's the only time that I've ever wanted to know who it was that said that so that I could like send them a disparaging note.
How rude.
Yeah, lame sauce. Total lame sauce. Like if you're going to come at me, come with something stronger than that. So learning to draw condensed structures and what the book calls skeleton structures. I hate that name, by the way. I much prefer, and you'll hear me call them bond line drawings. That is the correct name that the rest of the organic chemistry world uses for what they call skeleton structures. Call them bond line drawings. You'll sound a lot smarter, trust me. But we have to know these two different ways of abbreviating our drawings of organic molecules, because otherwise it would just take us for flippin' ever to draw these chemical structures. And the abbreviated ways are so much faster, particularly bond line drawings. That's the way that organic chemists like to communicate information. A little review of the shapes of molecules or molecular geometry is probably a good idea for us. Where did I have all these flare pens and I can't find them when I need them. Give me a second. it fell in the worst possible place, of course. And oh no, it dried up. And I don't even have a garbage can that I can huck my pens at in this room, which is really frustrating. Let's try the green one. Oh yeah, there we go. So polarity of bonds and then polarity of molecules as a whole. So this is something that we didn't learn how to do in Chem 121 or 161, but molecular geometry and polarity and how polarity relates to the properties of molecules, those are all topics that you have heard talked about at some time before, all right? So these are the topics that comprise most of what we want to understand from chapter 11, at least the parts that are the hardest for students to get. So let's do a little bit more practice with turning a Lewis structure into a condensed structure and then turning it into a skeleton structure, or I'm gonna just call them from now on, you'll hear me call them bond line drawings all the time, all right? Because I hate the term skeleton structure. When I teach how to actually draw a Lewis structure from scratch, I use the term skeleton structure for an incomplete like step on the way to your Lewis structure. And a lot of other chemistry professors do too. So skeleton is troubling in that context. So we'll call them bond line drawings. So when I'm finished with this, what I would like you guys to do is to turn this Lewis structure into a condensed structure and also to turn it into a bond line drawing. Whoever's got a lot of background noise going on, if you could mute yourself. I don't mind people not being muted. As a matter of fact, I want you to ask questions and interact. But if you have a lot of background noise, just you can always, if you're logging in through a computer, you can always just hold down your space bar to unmute yourself while you're asking a question. That's like a Zoom hack that's pretty awesome. I can't even make myself draw these very often because they're just so big and unwieldy, and they take for I gotta not see. I'm already trying to do condensed structures just because the full Lewis structures just take up too much space. All right, so let's try and draw that as a condensed structure and as a bond line drawing as well. Take a second and do that. Remember, condensed structures normally exist to take as many of the bonds themselves out of the structure as possible but maintaining all of the same structural information. So instead of those 3 covalent bonds, we condense that whole piece there into CH3. And then next door to that, we have a carbon that is bound to a hydrogen and another CH3. So we can represent that as CH, CH3. Actually, I don't like that at all. Let's try again.
I did CH and then in parentheses CH3 and then 2.
So the problem here is that having this carbon attached to both a CH3 and that O gets to be a little problematic when we're trying to figure out where the chain is going. So here's how I would handle that. Just because a condensed structure takes out covalent bonds doesn't mean it has to take out all the covalent bonds. I could write a covalent bond in here to a CH3 to show that that CH3 is branched. And then say that the hydrogen and oxygen were the other things attached to that second carbon there. The next carbon over has an oxygen attached to it, followed by a pair of CH2s. And then after that, if you ever have an issue with how you think your branching is going to work, it's perfectly acceptable to draw a few covalent bonds in to keep track of where your molecule is going. So as we read this, the CH3s, oh look, we could have even condensed this further because there are 2 CH3s bound to that second carbon. So we could have even done this if we wanted to.
That's what Candace said that she did, and that's what you said you didn't like.
No, that's not the problem. The problem is what's happening on the other side of this molecule. So if, you know what, I suppose that's, yeah, this is fine. This is fine. I don't think I was drawing it the way Candace was. I was trying to draw it yet another way that would have been not as clear.
Gotcha.
Candace, I'm sorry. I said that you were doing something wrong when you weren't. I affirm that you were on the right path. So something like that would be a great condensed form for this structure. Now, it's a little bit wonky to read what the types of bonds to these 2 oxygens are here, all right? So in cases like that, we could also have written this another way to make it clear that this carbon had a carbonyl group on it, a carbon double bound to oxygen. So if we wanted to make clear that that carbonyl group was a carbonyl group, we could have done something like this. Notice that I've also slightly changed the other end of that structure. Note that that carbon still has 2 CH3s and a CH2CH3 attached to it. This is yet another correct condensed structure. So the general idea with condensed structures is we're just taking out a lot of the drawn covalent bonds and just writing the atoms next to each other that are bound to each other, all right? That's a condensed structure. So Notice also that we have left out lone pairs on those oxygens. That doesn't mean that those lone pairs don't exist. We just have to remember that oxygen has to have 8 electrons around it. So each of those oxygens, this one being bound to each of the carbons, and this one being double bound to carbon here, each of those oxygen is going to end up needing 2 lone pairs in the full Lewis structure, like you see here. So now let's look at the bond line drawing version of this structure. So in the bond line version, carbons are left out and hydrogens are left out. Well, carbons aren't left out, they're not labeled, and hydrogens are completely left out unless they're attached to a heteroatom. So how do we maintain this same structure without showing the hydrogens? Well, I'll just draw the answer and then we'll talk through it. I don't have enough CH2s. Let's try again. Dr. Musk is slightly out of practice. I'll get better, I promise. I used to sing a little song for my majors organic students, count your carbons, name them one by one. It's similar to like an old Sunday school song for people that went to Sunday school when they were kids. 1 and 2, then the next one over is where we have our CH3s and our CH2, CH3. Okay, that is the correct bond line drawing, or a correct bond line drawing for that molecule up there. So where do we see all of the carbon atoms? In a bond line drawing, any end or any vertex represents a carbon, unless there's a heteroatom that's specifically written in, all right? So that's a carbon, and that's a carbon, and that's a carbon. Those represent those 3 carbons right there. So the carbon in the middle is the one that's bound to oxygen. That oxygen is bound to a carbon right there, which has a double bond to oxygen. And then we have a CH2 and another CH2. And then we have a carbon that is bound to a CH3 and another CH3, and then a CH2, CH3. So how can we tell how many hydrogens there are on each one of these carbons? We know that the carbons all have to have a full octet of electrons. So if this carbon is bound only to one other carbon, that stands to reason that it must have 3 hydrogens bound to it as well. The same thing is true here. This carbon is bound only to that carbon right here. So since that carbon only has 1 bond shown, it must have 3 bonds to hydrogen that are not shown. This carbon here has bonds to a total of 1, 2, 3, 4 other carbons. So because that carbon already has 4 bonds, we know that there are no hydrogens attached to that carbon. It takes a little bit of practice to be able to look at this and see how many hydrogens there should be attached to each one of those carbons. But if you watch these for a while, if you practice for a while, immediately when you look at this, you will get all of the same information that is in this Lewis structure, and it takes like 1/10 the time to draw. So that's why organic chemists like to communicate with bond line drawings, because they're way, way faster to draw and contain all the same information. Now, one place that you'll see a difference between the Lewis structure and the bond line drawing is I haven't drawn in lone pairs on the oxygen. Very often those are left out in bond line drawings, but not always. If you want to draw them in, that's also perfectly acceptable. As a matter of fact, very often I'll draw them in my bond line drawings, because these lone pairs on heteroatoms tend to be pairs of electrons that are important for how that molecule is going to behave. So let's do another example of turning a Lewis structure into a condensed structure and a bond line drawing, and I'll just give you a little bit to work and then give you the answer so you can check yourself.
Oh,
It'll be okay.
I'm out of practice, Dr. Must have been a year since I took your class.
All right, give it a shot. Remember, if you're having trouble condensing too much, it's always okay to show a couple of the bonds, especially in places where there's branching. All right. So here's how I would represent this with a condensed structure. And for a bond line drawing, so count your carbons and see if you can track all of the atoms from that Lewis structure into each one of those abbreviated types of structures, the condensed structure and the bond line drawing, what our book, in my opinion, erroneously refers to as the skeleton structure.
Dr. Musk,
Yes.
can you break down why you did everything the way you did it again?
So remember that skeleton structures just take bonds out and list the atoms as they are in order. So this if you wanted to say CH3 instead of H3C, same thing. Those hydrogens we know are attached to that first carbon either way. All right. So very often the very first carbon in a why can't My mind has completely gone blank. I can't remember the name of this kind of structure anymore.
Once I get to the CCH2, that's where I just like, I'm
This right
having
here?
a hard time. Yeah.
So the reason why that's hard is because there's branching at that carbon. So anytime there's branching in your structure, you are welcome to show some of the covalent bonds to show how the branching works. All right. In this condensed structure, that was the name that was like stuck out of my brain for just a second. All right. So branching in condensed structures is a time that we can show just a couple of covalent bonds to show where the branching happens. But this carbon is bound to oxygen, just like here. That oxygen is bound to the next carbon, just like here. So that carbon has 2 hydrogens attached to it, and then it's bound to the next carbon. And this next carbon is where our branching happens. And then we're bound to another CH2. And then this last carbon is where we have a double bond to oxygen and then an OH group. So that's very often abbreviated as COOH. So when you see a COOH in that, in this form of a structure, that is what we call a carboxylic acid. So that's the functional group that is represented by a double bond to oxygen and then an OH group. And remember that in a bond line drawing, any end, so an end or a vertex, an end of a line without any labels or a vertex counts as a carbon. So there's an end of a line. That counts as a carbon. And since there's only one bond coming out of that carbon, we know that that carbon has to have bonds to 3 hydrogens also. So this carbon right here is that CH3. And then we have an oxygen. Note that I could have decided to put my lone pairs in on that oxygen. You don't have to in a bond line drawing, but you have to remember that they're there, regardless of whether you write them in or not. So this oxygen is now bound to another CH2, and then we get to the carbon right here where the branching happens. So that carbon has bonds to 1, 2, 3, 4 other carbons. We know that there are no hydrogens attached, regardless of whether we write the hydrogens in or not. So not in the case of our bond line drawings. So this carbon is attached to the chain going this way, the chain going this way, and also to a CH3. So there's our CH3 and a CH2CH3, which is the group right here. Finally, we have another CH2 and then our COOH, the carboxylic acid. That was Mackenzie asking that question, right?
Ray.
Okay, so does
Yeah.
that make sense, Mackenzie?
No, it's Ray.
Oh, it's right.
Thank
I'm
you.
sorry. Does that make sense, Ray?
No, it makes a lot more sense now.
Okay, good. I'm sorry, I can only see a few of you at a time and not everybody has their videos on. So sometimes I'm just hearing things and I don't know exactly who's saying, but awesome. Hopefully that makes some sense. So those are a couple of examples of how we turn Lewis structures that take for flip and ever to draw into much easier to draw things. And if you're talking about the one that organic chemists like the most, it's definitely the bond line drawing. All right. It's all the information of a Lewis structure with the minimal amount of effort, especially for molecules with lots of branching. It's really easy to see the branching in the bond line drawing. And for complex molecules, it's a lot harder to see in the condensed structure. All right. But those are the ways that we abbreviate our Lewis structures to maintain all of the same information, but not take so long while we're writing them. So let's review a little bit about the shapes of molecules. And we've got some good molecules to look at to do that. So carbon can have several different shapes around it depending on its bonding pattern. So if a carbon has a triple bond and a single bond, that is a total of 2 electron groups coming out of that carbon. So carbons or any atoms that have exactly 2 electron groups coming out of them have a specific shape. Note that a carbon could also have 2 electron groups by having 2 double bonds coming out of it. So carbons with 2 electron groups, the farthest apart that those 2 electron groups can be is 180 degrees, which means that we call the shape around that carbon or this carbon linear. Now, we're not talking about carbons with unshared pairs of electrons, because for every molecule that we're going to be talking about with an uncharged carbon, that carbon is going to have 4 bonds and no lone pairs attached to it. All right, we'll talk about shapes around heteroatoms in just a minute. So another way that we could have a carbon with 4 total bonds is to have a carbon with a double bond and 2 single bonds. So since triple bonds or double bonds or single bonds, any of those counts as exactly 1 electron group, this example is a carbon that has a total of 3 electron groups attached to it. So atoms with exactly 3 electron groups have bond angles that are very close to 120 degrees. So the shape that we talk about for carbons with 3 electron groups, or for any atom that has 3 electron groups that are all bonding electron groups, in other words, no lone pairs on that central atom, we call that shape trigonal planar. And the reasoning behind that is, imagine that I'm not going to use real atoms here, but just assume that there are other atoms attached to each of these places. In that case, all 4 of these atoms, the carbon and the other 3 atoms, are all in the same plane, the same XY plane, and that plane forms the shape of a triangle. So that's why we call that shape trigonal planar. The final combination of bonds that we could have to add up to 4 total bonds for carbon is if carbon has 4 single bonds. Now, if you look at what the bond angles might look like by looking at this part of a Lewis structure, you might assume that that bond angle was 90 degrees, a quarter of the way around a circle. But that's wrong. The reason why it's wrong is we're assuming that all of these bonds are in the same XY plane. They're not. As a matter of fact, in order to represent that in 3 dimensions, we have to represent 2 of the bonds being in the same plane as my paper, and then 1 of the bonds coming out toward us, we represent that with a wedge, and 1 going away from us that we represent with a dash. So all of the bond angles around that carbon are identical, and they're all 109.5 degrees. So that shape is the shape of a 4-sided figure where all of the sides are identical in size. So geometrically, we call 4-sided figures with 4 identical sides tetrahedrons. So whenever we have a carbon with 4 single bonds around it, the shape that we call that carbon is tetrahedral. So an example of that would be methane, for example, CH4. So CH4 methane has a tetrahedral carbon for its only carbon. An example of a trigonal planar carbon would be found in a molecule like formaldehyde that has a central carbon bound to 2 hydrogens and then a double bond to oxygen. So that's an example of a trigonal planar carbon. An example of a linear carbon would be found in carbon dioxide. So now let's talk about shapes that we might see on some common heteroatoms. All right. So if we did a condensed structure that looked like this, I could even have taken these two bonds out and it would have been fine, but we're focusing on the shape around this oxygen. So you might be convinced that that oxygen is linear because it looks like there are only 2 electron groups attached to the oxygen. But we know, because oxygen has to have a full octet of electrons, that there are 2 pairs of electrons that are there, whether they're drawn in or not. So that oxygen in the center has 4 electron groups, because unshared pairs of electrons count as electron groups as well. So we just saw an example, methane, of a carbon with 4 electron groups. And to get those 4 electron groups as far apart as possible, we couldn't keep all 4 of them in the same plane. That's also true of this oxygen. So if we were drawing oxygen with 4 electron groups and respecting what its shape looked like, it would look something like this, where those unshared pairs of electrons would take up 2 of the electron groups, and then the CH3s would be approximately 109.5 degrees apart from one another. In reality, probably slightly less than 109.5. But 4 electron groups around that oxygen, anytime you're thinking about 4 electron groups, you're thinking of a bond angle around that atom close to 109.5 degrees. So what do we call this shape around oxygen? Well, if we're looking at the bonds themselves, we're talking about oxygen bound to 2 other carbons, and those 3 atoms don't form a straight line. So we can't call them linear. The shape around that oxygen is bent. Very, very similar to the shape that we would expect for water. 4 electron groups around that oxygen. So 2 of those 4 groups are the ones coming out at us and going back into the board, and the other 2 are the ones that are in the plane of the board. So a bond angle of about 109.5 degrees, about. What about the heteroatom nitrogen? Nitrogen's normal way of behaving in a Lewis structure, and these are great ways of looking at oxygen. So oxygen in organic molecules has 2 bonds and 2 lone pairs if it doesn't have a charge. Those are the only ones we have to worry about in this class. So you might see oxygen with 2 single bonds and 2 lone pairs, or you might see oxygen with 2 lone pairs and a double bond to carbon. We don't worry about the shape around that oxygen because there's only just a straight line, that double bond connecting to another carbon. Let's look at another shape that we can get for nitrogen. So nitrogen tends to have 3 single bonds and a lone pair. It's not the only way that we can see nitrogen. Nitrogen can have double or triple bonds also. But what would the shape be for this nitrogen with 3 single bonds and a lone pair? So imagine that we have a CH3 and a couple of hydrogens attached to that nitrogen. 4 total electron groups. So one of our 4 electron groups in this sort of tetrahedrally shape would be a lone pair. And then the remaining ones would occupy similar spaces to our picture for CH4 up there. So what do we call that shape around nitrogen? We can't call it tetrahedral because now our 4-sided figure is not all 4 identical sides. So instead you have to use your imagination a little bit. Around nitrogen, this looks like a 3-sided pyramid, all right? So, or a pyramid with a triangular base. So we call that shape around nitrogen trigonal pyramid. Some books will even use the adjective form of that, trigonal pyramidal. I just giggle every time I say that, so I don't. I just say trigonal pyramid instead. So those are the shapes that you're likely to encounter in organic molecules. Now, there are weird nitrogens out there, but if you remember how many lone pairs and how many total electron groups you have, you can still make sense of what their shapes are supposed to be. What if we had a weirdo nitrogen in a molecule that looked like this? I'm going to draw a bond line drawing of this molecule. So what if we had a nitrogen that looked like this? What's the shape around that nitrogen right there?
Would it be bent?
It is bent, all right? It's actually differently bent than water is, but it's still bent. So let's go through our analysis of this nitrogen. What things are attached to it? We have a lone pair, a single bond, and a double bond. That's a total of 3 electron groups attached to that nitrogen. So for things with 3 electron groups, we would expect the bond angle between bonds to be what, approximately?
109.5.
So 109.5 is the bond angle that we think about for things with 4 electron groups. In this case, there are only 3. That double bond counts as only 1 electron group, all right? No matter what kind of bond you have, if it's a single bond or a double bond or a triple bond, that counts as just 1 electron group. So we have a lone pair, that's 1 electron group. A single bond, that's a 2nd electron group. A double bond, that's our 3rd electron group. Things with 3 electron groups have bond angles 120 degrees. So it's still bent though, because whatever this atom is, in this case, a carbon, right? And up here, another carbon. Those 3 atoms are not in a straight line. We can't call that shape linear, so instead we call it bent. The geometry around that nitrogen is bent. Now, that's a pretty weird way of seeing nitrogen in a molecule. You won't see that in this class. We're not going to talk about this functional group particularly, all right? That's
Dr.
something called
Musk,
an enamine, which
if
we
that
don't have to worry
question,
about. Go ahead.
if that question came up for me, like for it to be bent and 120 degrees, that doesn't make sense to me. Like if that was in my homework, I wouldn't know how to solve that.
Okay, so what, by like, remove yourself from the context of chemistry. What does linear mean to you? A straight line, right? So if we're talking about a linear shape, we're talking about atoms that are in a straight line with one another. So the reason why CO2 has a linear carbon is because that oxygen and that carbon and that oxygen are all in a straight line. And that only happens when we have 180-degree bond angles. So these 3 atoms are not in a straight line. The same way that the 3 atoms that form water are not in a straight line. The difference is our bond angle here is 120 degrees, and our bond angle here, because of 4 electron groups instead of 3, is about 109.5. Both of them are bent because their bond angles around that central atom are not 180 degrees. So the only time we get into... Go ahead.
So bent can be 109.5 or it can be like 120. It's
Exactly.
like AEIOU and sometimes Y.
Yes, yes.
Okay.
So bent can happen anytime we have 2 other atoms bound to a central atom, but the bond angle isn't 180 degrees. That may be another way of explaining it that makes more sense. All right.
Thank you.
Yep. If you have 2 other atoms bound to that central atom, but the bond angle between them is not 180 degrees, your shape is bent.
The way that helped me understand when I talked to you, Mr. Musk, is that when you have that double bond, it counts as like 1 bond. So it's like there's 3 of them without, but has 4 technically bonds, but only has the 3 electrical groups, like what you were talking about. So with having just the 3 electrical groups, it brings it to that 120. But then if you have the 109, you have 4 groups.
Yep. So you can see that each one of those unshared pairs of electrons is an electron group. So that water has 4 electron groups around oxygen. So that's a nice little review of shape. All right, I'm glad that we got to that tonight. Gonna go back to my list and look at what else I wanted to cover. Polarity. All right, so I just posted videos that go into more detail about how we tell if a molecule is polar or non-polar. But what that has to do with is the concept of electronegativity. I'm looking around for a periodic table. I've got a, oh man, I think my cats got into this one. Look at that, it's a little bit messed up. I mean, it was a little messed up before because I wrote on it some, but then the cats messed it up even more. I don't know if that means they like chemistry or they hate chemistry, but whatever. So what's important here is in chemistry 121 or 161, one of the things that we talk about is this concept called electronegativity, which is how hard an atom pulls on its shared pairs of electrons. And for reasons that you might know more or less about, depending on which of those classes you took, the further up the periodic table and the further to the right on the periodic table we go, the more electronegative the atoms get. So out of all the atoms that actually form bonds on the periodic table, because the noble gases don't tend to form covalent bonds to anything except in very rare cases, out of all the atoms that are reactive on the periodic table, fluorine is the most electronegative atom, the one that pulls the hardest on its shared pairs of electrons. Now, if you've been out of chemistry for a while, you might have forgotten that hydrogen, in terms of its electronegativity, actually shows up right between boron and carbon. All right, so hydrogen pulls harder on its shared pairs of electrons than boron does, but it pulls less hard than carbon. And boron and hydrogen and carbon are all very, very similar to one another in electronegativity. So with that being said, we can estimate which atom is more electronegative by looking at the periodic table and seeing which atom is closer to fluorine on the periodic table. That's a rough approximation of which atom is more electronegative. All right, so that being said, let's take a look at a couple of covalent bonds and see how that affects electrons being shared. So what if we had a covalent bond between nitrogen and oxygen? That happens sometimes. Oxygen is closer to fluorine on the periodic table, so we know that it is the more electronegative atom. That means that oxygen is pulling harder on that shared pair of electrons than nitrogen is. The way that we draw that is by drawing a little arrow toward the more electronegative atom with a dash over the back of it. We call that a bond dipole. So that bond dipole points toward the more electronegative atom. This is basically like nitrogen and oxygen being a big brother, oxygen, and a little brother, nitrogen, sharing the same toy. All right? The big brother is going to hog the toy a little bit. So even though they both own that pair of electrons, oxygen is hogging it just a little bit. So that means that the oxygen here ends up with a slightly negative charge, and the nitrogen ends up with a slightly positive charge. That's what those delta signs mean from math. Delta is a representation of partial or tiny. So delta positive literally means partial positive or tiny positive. It doesn't mean that this nitrogen has a full positive charge. It just means that this pair of electrons is like slightly being stolen from that nitrogen. And this oxygen is slightly stealing that pair of electrons just a little bit from nitrogen. So when there's an atom of higher electronegativity with a covalent bond to an atom of lower electronegativity, generally speaking, we call those kinds of bonds polar covalent bonds because there's a slightly negative pole and a slightly positive pole. The electrons are not shared equally between those two atoms. One notable exception to this is the covalent bond between carbon and hydrogen. Even though carbon is very slightly more electronegative than hydrogen is, the difference is so small that we don't regard that as a polar bond. If we had a carbon with a covalent bond to oxygen, though, there's a big difference between those. It turns out there's a pretty big difference between carbon and nitrogen as well. So in each of those cases, the heteroatom is more electronegative than carbon is. So our bond dipole points toward those more electronegative atoms, and each of those is a polar covalent bond. So a slightly negative side and a slightly positive side. That's why we call them polar covalent bonds. So in molecules like alkanes, so I'm going to draw a 4-carbon alkane in chapter 12. We'll realize that that is called butane. So CH3, CH2, CH2, CH3. In alkanes like that, the only bonds that we see are bonds between carbon and bonds between carbon and hydrogen. So there are no polar bonds in that molecule whatsoever, which means that we call that molecule a nonpolar molecule. In molecules where there are one or more polar covalent bonds, it is possible that the entire molecule can be polar as well. So here's an example of that. Let's look at methanol, CH3OH. If we draw the bond line drawing for methanol, it just looks like this. So that end of a line right there is a carbon, and because there's only one bond coming out of that carbon, we know that there are 3 hydrogens that are not being shown. Now, if we draw in the important covalent bonds around that oxygen, we know that that oxygen has a total of 4 electron groups. If we draw in the bond dipoles, because oxygen is more electronegative than carbon and also more electronegative than hydrogen, the bond dipoles both point up toward oxygen for those 2 polar covalent bonds. So if we're looking for the direction that those bond dipoles are pointing, they're both pointing up toward the oxygen side of the molecule. So if we average those 2 directions for those bond dipoles, the net dipole for all the polar bonds here is pointing up toward oxygen. Now, what does that tell us? That tells us that this entire side, the oxygen top side of this molecule, is slightly negative. It has a slightly greater electron density than the other side of the molecule that has slightly less electron density. So in cases where the bond dipoles point in a net direction, there's one side of the molecule that's slightly more negative and another side of the molecule that's slightly more positive. We say that this is a polar molecule. So that is methanol. Methanol is a polar enough molecule that it actually dissolves very well in water. That's one of the reasons that we talk about whether molecules are polar or nonpolar, is because polar molecules dissolve well in polar solvents and nonpolar molecules dissolve well in nonpolar solvents. So all of you have heard oil and water don't mix. Why don't they mix? Well, because water is a very polar solvent and oils are things like alkanes that are very nonpolar. All right, like dissolves like. It is possible to have polar bonds in a molecule and still have the molecule be nonpolar. Let me give you a couple of examples of that. These are both molecules that have polar bonds, but they are nonpolar molecules. So see if you can draw good Lewis structures for CF4 and CO2. And I'm going to go ahead and draw those in the actual 3-dimensional shapes around that central carbon. Note that in this case, in both of these cases, each of the bonds in these molecules are polar bonds. They're bonds between atoms of very different electronegativities. Fluorine is much more electronegative than carbon is. So all 4 of these bond dipoles are pointed out from carbon toward those 4 fluorines at the periphery. In this case, 180 degrees apart are the bond dipoles pointing out from carbon toward those 2 oxygens. So the difference here is that if we look at the directions those bond dipoles are pointing, there isn't one net direction that they're pointing, sort of spaced out evenly. Here, they're actually directly opposing one another, all right? Those 2 bond dipoles are 180 degrees apart. They cancel each other out. So if we look at this pair of bond dipoles, those 2 are pointing in this direction, whereas these 2 bond dipoles are pointing, well, 180 degrees apart in the opposite direction. In each of these cases, the bond dipoles don't point in one net direction around the molecule. There's not one side of CF4 that's more negative than the other side. There's not one side of CO2 that's more negative than the other side. Each of these molecules has polar bonds, but they are non-polar molecules. So when we talk about polarity, we can talk about the polarity of a bond, right? That bond right there is a bond between atoms of different electronegativities. So it's a polar bond. When we're talking about whether a molecule is polar, we're talking about whether the bond dipoles all point to one side of the molecule. If there's a whole side of the molecule that has more electron density than the other or not. In this case, there is no place where those bond dipoles are pointing, all right? So they're both non-polar molecules. Is that helpful? I know you guys have all heard those words before in earlier contexts, but you know, like Juan said, it's been a while for some of us. It's even been a couple of weeks for me since I've thought about this. So it's good for us to revisit it. Any questions? I don't know that if that silence is a blessed silence or a cursed silence, but we'll just take it for what it is for right now. That's good. So one of the last topics from chapter 11 is, in order to understand organic chemistry, you have to understand that there are small parts of molecules that have characteristic ways of behaving. We call them functional groups. So the reason why us being able to identify functional groups is important is because certain functional groups always behave the same way in molecules, all right? So the simplest class of organic molecules are ones without any functional groups at all. They are called alkanes. They have nothing but carbon-carbon single bonds and carbon-hydrogen single bonds in them. So this is a molecule called cyclohexane. That is a ring with 6 total carbons in it. And if you look at each one of those carbons, there are 2 bonds shown. So how many hydrogens are there on any one of those carbons in that ring? It's the same answer for every one.
5.
12.
There are 5 hydrogens on each carbon there?
2.
Oh, 2 each
Altogether it
for
should be
2
12.
each.
2 each. Yep, 2 each. So if there are 6 total carbons, that means for the whole molecule there be
12.
12 hydrogens, right? Yeah, so each one of those carbons has 2 hydrogens attached to it. But this molecule, by saying it doesn't have any functional groups, that's another way of saying it's really boring, all right? It really doesn't do anything. It's hard to change cyclohexane, this molecule, into another molecule because there isn't any functionality. The carbon and hydrogen single bonds don't really have very much reactivity to them at all right? So if we get to slightly larger molecules or ones with a little bit more diversity in the way the bonding works, then we have some reactions, some things that we can do to them to transform them into other molecules. So let's look at some functional groups in molecules. Any place that we have a carbon-carbon double bond in a molecule, we call carbon-carbon double bonds alkene functional groups. So an example of that would be something like this, or like this. The reason why it's important for us to learn those functional groups is because wherever we see a carbon-carbon double bond show up in an organic molecule, immediately, once you get really good at organic chemistry, you know some ways that we can take that carbon-carbon double bond and react it to change it into other types of functional groups. All right? So there are characteristic reactions of alkenes, carbon-carbon double bonds. Any place that we have a carbon-carbon triple bond in a molecule, we call that an alkyne functional group, A-L-K-Y-N-E. Now, don't be one of the people that draws alkynes in a funky way. So if we have a carbon-carbon triple bond, the only thing that's left over is one other electron group attached to each of these carbons. So each of those carbons in an alkyne always has a linear geometry. So if I were drawing this molecule, how would I turn that into a bond line drawing? Take a second and see if you can turn that into a good bond line drawing. The correct answer is either very satisfying or very unsatisfying, depending on like how long you've been staring at it. So here is the correct answer for how we would change this into a bond line drawing.
Yay.
The not
That's
correct answer, or at least the answer that has incredibly poor taste, would be something like this. That is the correct arrangement of atoms. That is a carbon with 3 bonds. So there's 1 hydrogen there, no hydrogens there, and 3 hydrogens there. But we know that that middle carbon is linear. So when we draw our bond line drawings, we want to at least attempt to maintain the correct bond angles for the carbons. So that's why this is good. And that like makes me want to throw up in my mouth just a little bit. But anytime we have carbon-carbon triple bonds, that functional group is an alkyne functional group. All right. If we happen to have a 6-carbon ring with what look like alternating double and single bonds in it, that is called a benzene ring. And it is one type of something that we call aromatic rings. So we're not going to talk about aromaticity in this course very much. It's kind of a complex topic, but just remember from Chem 121 or 161, what we talk about when there's more than one way to draw the bonding between atoms. If we draw that benzene ring like this, we could also very easily share the electrons this way in that benzene ring instead. So since there are two identical ways of drawing the bonding around that ring, what that means is that neither one of these is a perfectly accurate way of representing the bonding. It's actually a hybrid of both of those. They are two resonance structures of one another. So even though in benzene, what we see when we draw the Lewis structure out, or the bond line drawing, it looks like a carbon-carbon double bond, then single, then double, then single, then double, then single. In reality, benzene doesn't have any carbon-carbon double bonds in it at all. And it doesn't have any carbon-carbon single bonds in it at all. Each of these bonds is actually a carbon-carbon 1.5 bond. That's what resonance tells us. So anyway, when you see these benzene rings show up in molecules, they have characteristic reactivity and behavior. They're called aromatic rings because lots of molecules with benzene and other aromatic rings in them have pleasant aromas. All right. Benzene itself smells slightly sweet, but you don't want to smell it for too long because it's carcinogenic. If we add a CH3 to benzene, it becomes toluene. We'll talk more about how to name these later on, but toluene is noteworthy because it's actually what gives gasoline its characteristic, like slightly sweet smell. So if you're smelling gasoline at the pump, you're smelling toluene. It's one of the most fragrant components of gasolines. So let's talk now about some functional groups that have heteroatoms in them, all right? First of all, if we have oxygen showing up with two single bonds, the two single bonds could be to two carbon-based groups, like in this case, and we call that functional group with an oxygen bound to two carbon-based groups. So if we just want to give a general form for carbon-based groups, we can use this notation, R. That means the rest of the molecule. So having two carbon-based groups attached to an oxygen makes this an ether functional group. Ether, not ether. If one of those two attachments to oxygen becomes a hydrogen instead, then our functional group is not an ether. Instead, it is an alcohol functional group. So an example, the preeminent example of the alcohol functional group happens to be this molecule, ethanol. So that's what is in alcoholic beverages. This molecule, and we'll talk more about naming later, that is isopropanol, all right? So the stuff that we have in antiseptic wipes, for example. Everybody good with those? I kind of want to use another page so I can, all right, sweet. My phone is blowing up right now. What is going on? It's like the world's on fire. I wonder if like protesters are trying to take over our capital or something. Oh, wait.
It was already happening earlier.
I know, it was a joke. I was trying to keep everything light today. I know there's a lot of heavy stuff going on in the world. I was trying to be deadpan there. Sorry for the dad humor. I'm not even
nailed it.
but I've got the dad jokes for days.
Bring him on.
Okay.
Yeah, right. I'm into it.
List, not because I don't have all the functional groups memorized, but just I don't want to forget to mention any of the ones that our book talks about. Actually, on page 384 and 385 of the text is a great little chart that has the ones that are important for us. All right. And then I think 386. Yep. So 384 to 386, that list of functional groups is basically all the ones you're going to need to know for my class. So let's go through examples of the rest of them really quickly. We've talked about alcohols and ethers. So very similar to an alcohol, if we have a sulfur bound to an alkyl group on one side and a hydrogen on the other, that looks a lot like an alcohol, except with a sulfur instead of an oxygen. So instead of an alcohol, we call that a thiol. The characteristic property of thiols is their smell. They smell disgusting, like rotten eggs. All right. So you guys have probably, are there skunks on Whidbey Island? I don't know if there are skunks on Whidbey Island, but skunk stink is actually this molecule primarily.
Driving by the cannabis stores, yeah, it smells like skunk.
Yeah, well, cannabis is not a thiol, but those molecules do have a very skunky aroma sometimes, right? But most of the low molecular weight, the small thiols, have that sort of skunky smell to them. So this is one more carbon. That's butane thiol.
What about like skunk cabbage, like the plant? Would that?
I honestly don't know for sure if it's a thiol or not, but it would not surprise me at all. So rotten eggs have rotten eggs don't have a thiol in them, but they have SH2, which is like akin to water, but with sulfur instead. So SH2 has that same odor as well. So that's rotten egg smell. Anytime we have some sort of an alkyl group that is attached to a halogen of any kind. So halogens are normally abbreviated with an X. So that X could be a fluorine, a chlorine, a bromine, or an iodine, any one of those. We call any of those alkyl halide. I'm getting sort of a buzzing sound from somebody. If you're not muted right now and you're not asking a question, mute yourself so that we can try and get the background noise to a minimum. Thank you very much. I appreciate that. If we have, this one's a little bit harder, all right? So nitrogens can be tricky because a nitrogen can be in several functional groups. So if we have a nitrogen that is attached to anywhere between 1 and 3 alkyl groups. So for example, if we had a CH3 and 2 hydrogens attached to a nitrogen, that would leave a lone pair on the nitrogen. That is one example of this type of functional group. Or we could have 2 alkyl groups and 1 hydrogen attached to a nitrogen. Or we could have 3 alkyl groups attached to a nitrogen. These are all versions of the same kind of functional group. We call them amines. So this, a molecule with only 1 carbon attached to that nitrogen is a primary amine. A nitrogen with 2 alkyl groups attached is a secondary amine. And a nitrogen with 3 alkyl groups attached is a tertiary amine. But they're all versions of that amine functional group. And then finally, we have a number of different functional groups that all contain this same part to them. All right. So all of these now are functional groups that have a carbon-oxygen double bond. The nickname that chemists give to this carbon-oxygen double bond is a carbonyl group. So the carbonyl group isn't a functional group, but it is part of a lot of functional groups. So where can carbonyl groups show up? If we have a carbonyl group that sits in between 2 alkyl groups, that forms a functional group that we call a ketone. So here's the simplest ketone that I can think of, a ketone where our carbonyl group has a CH3 on each side. You've probably heard of this solvent before. The common name for that is acetone. If we have an alkyl group on one side of our carbonyl, and then on the other side, a hydrogen, that functional group is an aldehyde. As a matter of fact, it doesn't even necessarily have to be an alkyl group on one side. If we have a carbonyl group and a hydrogen on one side of it, it's always an aldehyde. The simplest aldehyde is the aldehyde that has 2 hydrogens attached to that carbonyl group. So that aldehyde is formaldehyde. So in aqueous solution, formaldehyde is used to embalm dead people. If we have an alkyl group bound to a carbonyl, and then on the other side, an OH group, that functional group is called a carboxylic acid. So one of the simplest carboxylic acids is one where we have a CH3 bound to our carbonyl group, and then with the OH on the other side. The common name for that molecule is acetic acid. So acetic acid is the carboxylic acid that's present in about 3 to 5% concentration in vinegar. And it turns out that carboxylic acid functional groups actually make molecules taste very sharp, all right? So you guys all know what acetic acid tastes like, a nice sharp bite. Very similar is citric acid found in lemon juice or orange juice, right? So carboxylic acids tend to have that very bright, like sort of slap on your tongue. We're almost done, only a couple more to go. These ones are kind of difficult. So if we have a carbonyl group with a nitrogen on one side. Now, you have to sort of fill in the rest. We could have a hydrogen over here, more commonly some sort of alkyl group. And then what else is attached to this nitrogen? It doesn't really matter, okay? So we could have a couple of alkyl groups attached, or a couple of hydrogens, or some mixture thereof. But anytime we have a carbonyl group and a nitrogen attached to it, we call that functional group, I refer to that as an amide. There are other people with PhDs in chemistry that call this an amide. So either pronunciation is perfectly acceptable. I prefer amide personally, all right? But either one is okay. I'm just trying to make you guys sound smart when you talk about these later. So don't call it an ether because nobody does that. It's an ether, right? In this case, if you say amide or amide, you'll sound smart either way. And then finally, very similar to a carboxylic acid, but instead of having an OH group attached on one side of the carbonyl, we have an oxygen that is bound to another alkyl group. We call these molecules esters. That's an ester functional group. The cool thing about esters is that a very large number of them that are small esters actually have very pleasant, fragrant aromas to them. All right. So if you look in the book, you'll see pictures of a number of different esters that are like sort of a distilled fruit smell. They tend to have very fruity smells, the smaller ones. One of my favorite labs that we do when this class is held in person is the week where we make a number of different esters by doing chemical reactions and then sniff them to try and figure out what fruit flavor they smell like. It's really fun. I'm going to be crying the week that we're supposed to be in lab doing that one because I miss having you guys in there. All right, that's our list of functional groups that I want you to remember. All right, start memorizing those now because it takes a little while. This is also probably, we've been going almost an hour and a half, probably a good time for us to like shut her down for the night. So when we come back next time, the first thing that I'm going to try and do is I'm going to try and draw or look at some pictures of bond line drawings. and we'll try and pick out the functional groups in them. That'll be some really good practice, all right? If you go to the back of the chapter where the homework problems are, you have lots and lots of bond line drawings pictured. Look through those and see if you can identify functional groups in some of those molecules. That's the best way to practice that. Any questions before we're done? Man, I can't believe it. My voice is already tired. I've only been talking for an hour and a half. I got to get my voice back in shape again.
Did you see? Sorry, did you see Pelosi's desk?
I did. Let's not talk about politics too much. I want to keep this an inclusive environment where everybody feels welcome. But yes, I did. It was.
Did you see the fortune cookie?
No, I didn't see a fortune cookie.
She has, I'll send it to you over email or something. She has a little taped up fortune cookie fortune, which is so funny, in like wrapping paper.
Have any of you guys ever gotten a bad fortune in a fortune cookie? No? Yeah, they're supposed to be like uplifting, right? I've gotten 2 bad fortunes in fortune cookies in my life. As a matter of fact, like yeah, when I was in high school, one of my teachers gave me a fortune cookie in class and was like handing them out for fun to all the students to give them like a little treat. And somebody remarked that it would be so funny if there was a possibility of having a negative fortune, right? And Mr. Beach, the teacher, was like, I've never had a negative fortune, and I don't think it's even possible. Well, I opened the fortune cookie, and it was something like, watch your back, or something like that. And I just like immediately started crying, laughing, and brought the fortune up to Mr. Beach. And then Mr. Beach just lost it when he saw that negative fortune. And I've gotten another one. So I don't regard myself as a particularly unlucky person, but I have been lucky enough to get bad fortunes a couple of times. So I don't know what that means, but anyways. Anime, did you have a question? I saw that you, oh, never mind. That was just my cursor. I'm looking at the chat. Yeah, Candace, I'm sorry about that. I don't know what's going on, but if my audio ever breaks up and you need me to repeat something, please just let me know, and I'll definitely do that, okay? We're all doing our best.
I think it's the screen sharing. I've noticed if you tend to have issues, if you close down your screen, it might load a little faster, but I think it might have to do with your screen sharing, Musk, just because I was having issues with it earlier also.
Yeah, that's a Zoom thing, not just a me thing.
Yeah.
So if you ever have me cut out for something important, just have me repeat myself. I don't mind doing that at all. All right.
Perfect.
Okay. If you guys have any more questions, I do have office hours tomorrow from 2 until 3:30. So please pop in and get those questions answered. If you can't come to office hours that early, are you just going to be like, well, I guess I'm defeated. Musk doesn't have office hours I can attend. No, you're going to text me on my cell phone and say, I can't come to any of your office hours. Can we set up a time to chat? And I'll be like, heck yeah, when are you available? All right. So I want to be able to help you, but don't get stuck just because you can't come to something or other. Definitely let me know if you need help and I'll reach out. All right. Okay. I'll see you guys next Monday, unless I see you in office hours before. All right. Have a wonderful rest of your week, everybody.